Understanding the Big Bang and the speed of light, the Big Bang theory is the most widely accepted explanation for the origin of our universe. According to this theory, the universe began as an extremely hot and dense point roughly 13.8 billion years ago and has been expanding ever since. This expansion created not only all matter and energy, but also space and time themselves. However, many people find it puzzling that, shortly after the Big Bang, certain parts of the universe seem to have moved away from each other faster than the speed of light. This appears to violate a core principle of Einstein's theory of relativity, which asserts that nothing can travel faster than light in a vacuum. So, did the Big Bang really outrun the speed of light, and if so, how can that be explained? To answer this question, it's important to distinguish between two concepts: motion through space versus the expansion of space. When Einstein stated that nothing can move faster than the speed of light, he was referring to objects moving through space, not the space itself expanding. The speed of light's approximately 299,792 kilometers per second sets a cosmic speed limit for matter, energy, and information. However, the fabric of space-time is not bound by that same limitation in the same way. This distinction is key to understanding how the universe could expand faster than light without breaking the laws of physics. Faster than light expansion of space. Just after the Big Bang, the universe underwent a period of incredibly rapid expansion known as cosmic inflation. This happened within the first tiny fraction of a second, specifically, from about 1036 to 1032 seconds after the Big Bang. During this period, space expanded exponentially, meaning the distance between 2 points in the universe increased at an enormous rate, far outpacing the speed of light. It's crucial to understand that nothing was moving through space faster than light during inflation. Instead, space itself was stretching. Imagine dots on a balloon. As you blow up the balloon, the dots move farther apart, not because they're moving on the surface, but because the surface itself is expanding. Similarly, during cosmic inflation, points in the universe were driven apart not because matter was flying through space at superluminal speeds, but because the space between them was expanding faster than light could travel. This concept doesn't violate relativity because special relativity prohibits information or matter from moving through space faster than light. But it doesn't limit how fast space itself can grow. During inflation, regions of the universe became causally disconnected, i.e., they could no longer influence each other because light couldn't travel fast enough to keep them in contact, which helps explain the large-scale uniformity of the cosmos observed today. Hubble expansion and the observable universe. Even after the inflationary period ended, the universe continued to expand, although at a much slower rate. This ongoing expansion is what we measure today with the Hubble constant, a value that tells us how fast galaxies are receding from each other as a function of their distance. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship is not because galaxies are zooming through space at high speeds, but again because space itself is stretching. At very large distances, this expansion results in galaxies receding from us faster than the speed of light. For example, galaxies more than about 14 billion light-years away as measured in terms of present-day distance are currently receding from us faster than light due to the expansion of space. These galaxies are not observable by us anymore because their light will never reach us. This leads to the concept of the cosmic horizon or observable universe, the maximum distance from which light has had time to reach us since the Big Bang. This doesn't mean that those galaxies are breaking the rules of physics. It means that the rules must be understood within the framework of general relativity, which governs how space-time behaves on large scales. In this model, the expansion of the universe can indeed outrun the speed of light without any contradiction, because we are not dealing with the motion of objects within space, but rather the expansion of space itself. Misconceptions about the speed of light in the universe, the confusion surrounding faster than light expansion arises mostly from the way we interpret velocity and distance in our everyday experience. In our normal lives, speed is always relative. We can measure how fast a car moves along a road. But in cosmology, we are dealing with the stretching of the very framework that defines distance and time. The expansion of the universe is not like a car driving on a road. It's more like the road itself growing longer, carrying the car with it. Another common misconception is that the Big Bang was like an explosion in space. In reality, it was an expansion of space. There was no center of the explosion and no pre-existing space into which it expanded. Every point in the universe was once condensed into an unimaginably dense state, and the expansion occurred everywhere at once. That's why when we look in any direction with telescopes like the James Webb Space Telescope, we see galaxies receding. And we're essentially looking into our own past, a timeline of the universe unfolding as light reaches us from farther and farther distances. These ideas challenge our intuitive understanding of motion, but they are well supported by observational evidence, including the redshift of galaxies, the cosmic microwave background radiation, and large-scale structure formations in the universe. All of these observations point toward a universe that is not only expanding but once expanded faster than light, and continues to expand in ways that make parts of it permanently unreachable. The universe and its limitless expansion. So, did the Big Bang outrun the speed of light? In a very real sense, yes, but not in a way that violates physics. The early universe, during the phase of cosmic inflation, expanded so rapidly that regions of space were pulled apart faster than light could travel between them. Even today, due to the continued expansion of space, galaxies far enough away are receding from us faster than the speed of light. This is all entirely consistent with Einstein's theories because it's not objects moving faster than light through space, it's space itself expanding. Understanding this requires a shift in thinking from the everyday notions of speed and distance to the deeper, more abstract geometry of space-time. Cosmology doesn't just ask how fast things are moving, but how space itself behaves on the grandest of scales. When we take that into account, the idea of faster, then light expansion becomes not only acceptable but essential to explaining how the universe looks today. In conclusion, the Big Bang and the expansion of the universe showcase the remarkable flexibility of space, time, and the limits of classical physics. It also highlights the incredible progress science has made in understanding the cosmos, from a tiny, hot singularity to an immense, ever-growing universe. While the idea that something could outrun light may seem paradoxical, it's a testament to the power of human curiosity and theoretical physics that we can now describe such phenomena with clarity and confidence.